Hi everyone, we're looking at 4.3 today, looking at how the first derivative and the second derivative can tell us things about the shape of the graph of the function. All right, let's get started. So the first thing is the first derivative test. So the idea here is, up until now, you've been figuring out your critical points, and we haven't really had a great way to determine whether those critical points are mins or maxes or neither. So what we've been doing in the first couple sections is finding what the critical points are, and then kind of just depending on the graph, kind of looking at the picture and going, oh, it looks like it must be a minimum and the other one must be a maximum. So if we want to be able to figure out whether our critical points are mins or maxes without looking at the graph, because maybe the whole point is to draw the graph, then we can use something called the first derivative test. So the idea is you still go about finding your critical points, and then you're going to put them on a little number line, and you're going to check on either side of the point for the slope and see whether the slope is positive or negative. So the idea is, if it's positive, then we know from the previous section that the graph is going uphill, or it's an increasing function in that domain. And then the part that has a negative slope, it must be going downhill. So if it goes from uphill to downhill, then that would give us a maximum. And vice versa for minimum, if it was going downhill on one side of the critical point and then uphill on the other side, going downhill on the left, uphill on the right, that would be a minimum. So let's give this a try. So here's our fourth degree polynomial. I went ahead and took its derivative and factored 4 out just to make things look better. And then I grabbed my calculator and just hit solve, and I got 3 values here. So again, I don't think that this is going to be something I want to try to solve by hand. So I just use the solve function on my calculator. I get those 3 values. So these become my critical numbers. I have 3 of them. So I go ahead and put them on a number line. And I know that the derivative is 0 at each of those places. There's nowhere, by the way, where the derivative doesn't exist, since it's just a cubic for my derivative. So anyway, I have my 3 numbers on my number line, and now I'm going to try to get these pluses and minuses. So I pick a number, let's say in this section, let's say I'm trying to figure out that this is negative. So I'd pick a number somewhere in here, let's say 0, and I would plug it in, and I would see what the sign turned out to be. So it would turn out negative, and that's my negative sign. I could pick a number over here, let's say like 1, plug in 1 and see, oh, it turns out that my derivative is positive there. So again, these pluses and minuses I'm getting from plugging a number in to my first derivative, not the original function, but the first derivative. So once I have my signs laid out, I then picture going uphill to going downhill. That means at negative 0.532, I have a maximum. And then it goes from downhill to uphill, so that must be a minimum. Over here on the graph, I went ahead and showed it with the different colors. So every time my function was increasing with a plus in my chart, it's red. And when the minuses occurred, I made them blue. And I know that at this point, since it goes red to blue, it must be a maximum. This one up here also, red to blue, must be maximum. This one down here, blue to red, must be minimum. Okay? So we don't have to necessarily look at our picture, and we can just look at whether it goes plus to minus or minus to plus and tell whether it's a min or max. That's the first derivative test, since it uses the first derivative. You have the second option. If you don't like the first derivative test for whatever reason, you can use what we call the second derivative test. The second derivative test means you're going to have to actually find the second derivative. So you would calculate out your second derivative, set it equal to 0, and you'll get your what we call points of inflection. And then you're going to put the points of inflection, well, actually, I'm getting ahead of myself. So if you just take a look at your second derivative, and we already have our critical numbers. So if you already kind of know that these critical values are places for mins or maxes, the idea here is that if your critical point is on a section that's concave down, it must be a maximum. And if your critical point is on a section of the curve that's concave up, it must be a minimum. And the concavity is determined by the second derivative. So if I take a look at my second derivative, plug in the value that I got for my critical number, if what I get is positive, I know my function's concave up there, and it must be a local minimum. Same idea for max. So let's try this with the same function that we were looking at a minute ago. So here's my fourth degree, and these are the same critical numbers that I had already figured out on the other slide. So if I go ahead and plug my my 0.532 my critical number, into the second derivative, it'll turn out negative. And so again, my conclusion then is that since it's negative, it's concave down there, and I must have a local max there, which again, the y coordinate, not the x coordinate, so f of that is the y coordinate, would be a maximum. Same idea here. This is my other critical point. Plug it into the second derivative. It turned out positive. And since it's positive, my function's concave up. I must have a minimum there. Again, f of the critical number gives me the y coordinate. It's the y coordinate that we refer to as the extreme value. Same idea on the last one. Okay, so that's the first derivative test and the second derivative test. Let's see, I went ahead and showed graphically the same function that we've been looking at. If I go ahead and take my second derivative and figure out where my second derivative is 0, I get 0 and 2. Those are what we call points of inflection, places where the second derivative is 0. Points of inflection are going to be the places where the concavity changes. So if you look in your at the graph here when x is 0, you can tell it's shaded below here in gray. It was concave down up until x equals 0. And then here it's shaded in gray above the curve. It's concave up in that stretch. And then after x being 2, it goes back to being concave down. So if we're interested in just the concavity, like where is it concave up, where is it concave down, that kind of thing, then I'm going to take my second derivative, set it equal to 0, and then I'm going to do a similar little number line, only I'm going to be checking my second derivative, plugging some test points into y double prime and telling whether the sign is positive or negative, and drawing the conclusion that when it's negative, it's concave down, when it's positive, it's concave up. And the place where the sign switches from minus to plus or plus to minus is our point of inflection. Now I have to warn you, sometimes when you do these little sign charts, you put the places where the second derivative is 0 or does not exist on your number line, and you start checking your signs. Sometimes your sign doesn't change. It goes from positive on one side to still positive on the other side. If that happens, we do not refer to this as a point of inflection. The point of inflections only are when the sign changes. So you have to kind of be a little careful with that. Okay, so here's another example. I have a nice rational equation, and I'm just going to practice finding everything. So we're going to try to figure out when is it concave up, when is it concave down, when is it increasing, when is it decreasing, what are the points of inflection. I guess I didn't list mins and maxes, but we'll do everything else. Well, maybe I did do mins and maxes anyway. Okay, so here I took my derivative just with quotient rule. I won't go through all that, but I simplified it down. I got to here. So if I'm looking for when what the critical numbers are, I'm going to be taking the first derivative and setting it equal to 0. So that's what I did over here. I'm just interested in the numerator being 0, and I factored it out. I got 1 and negative 1. Are there any places where the derivative does not exist? Well, here I have a positive number, something squared, adding a 1, quantity squared is definitely positive. There is no way that the denominator is going to be 0, so I don't really have anywhere where the derivative doesn't exist. So my only critical numbers are going to be when x is 1 and negative 1. So I put them on a number line, and I start checking my first derivative for around those values, and it goes minus, plus, minus. So again, that means if I'm picturing at x equals negative 1, am I going to get a min or a max? Which one is it? Well, negative to positive means it's going down and then going up. It must be a minimum. And then over here, when x is 1, it went from going up to going down. That must be a maximum. Okay, intervals where it's increasing and decreasing, well, the minus, anywhere that you have the minus in my chart, would be the intervals where it's decreasing. The plus would be the interval that it's increasing. So from minus 1 to 1, it's increasing. Anything bigger than 1 or less than minus 1, it's decreasing. So still same equation, trying to move on to the concavity and finding points of inflection. So I had to do my second derivative. So again, if I back up a little bit, here was my first derivative. It was a rational function. So I'm going to have to do quotient rule again to get the second derivative. So look how fun that is. So I'll just cut to the chase. Here's what I got when I simplified it. So we're looking for points of inflection, let's say. So I'm going to take my second derivative and set it equal to 0 and solve. Again, you can multiply through by the denominator, it goes away. I'm just interested in the top being 0. It happens 2 places, or actually 3 places when x is 0, root 3, and negative root 3. So those are going to be my possible points of inflection. So I put them on a number line and I check my signs around them, and sure enough, all three of them do turn out to be points of inflection because the signs are changing at each of those points. So it's going to be concave down right here, concave up in this section, concave down, then concave up again. So I went ahead and graphed my original function. So this is a picture of y, and hopefully all of this is piecing together with my picture. So it should look concave down up until negative root 3. So this portion over here would be concave down. It looks like a frown. And then somewhere along the way it switches to looking like a smile. And that would be at negative root 3. So wherever that is on my number line, negative root 3, somewhere in here, it's going to switch to being concave up. And then at 0, it switches to being concave down, looking like a frown again. And then it kind of looks again like a smile at the very end, concave up. Okay? All right, that's a lot. The good news is that's not just a lot, but that's everything. So I mentioned, I think, in class earlier that sections 1, 2, and 3 of chapter 4 all go together. It's all kind of building one on the other. So you will have a quiz on sections 1, 2, and 3. And really, if you can do this last problem, you can pretty much do your quiz. Also, this practice problem, same kind of thing. I'm going to give you one function and ask you to find everything there is to find about the function. Where is it increasing and decreasing? Where is it concave up and concave down? What's the point of inflection or points of inflection? And your extreme values, which of course means you're going to have to find your critical numbers. So if you can do all of that, you're set for your quiz. So here's your practice problem. Give it a try. Consider it a practice quiz. And when you're ready, go ahead and unpause. Okay, so I went ahead and took my first derivative with product rule, and because it had some negative exponents, I went ahead and wrote it as a fraction or a rational expression, and tried to clean it up as best I could. So here's my first derivative as best I could get it. So for starters, I'm going to go ahead and do my little chart that I've been doing all chapter long, finding where my derivative is 0 and where it doesn't exist, and are there any endpoints. So there's a couple values here where the derivative is 0. I looked at where the derivative does not exist. It's going to be at 3 and negative 3, but those actually are my endpoints as well. If I back up for a second, here's my original function. It has a root in it, and I know that there's values that will make my root negative. And so my domain of my original problem is just trapped between negative 3 and positive 3. So even though it didn't give me an interval, I know that the domain of this problem is minus 3 to positive 3. So the endpoints really are negative 3 and positive 3. If I plug those into my original function, I get 0 for the y-coordinates. So I go to my number line and I put all these critical numbers, as well as kind of keeping track that I have endpoints here. So I'm only looking at the portion of the domain from minus 3 to 3. And then I start checking my first derivative signs. And again, here's my first derivative. I'm just plugging in some test values in each interval and seeing whether it's positive or negative. So anywhere that came out positive, I know my function is increasing. Negative means that my function is decreasing. And I can go ahead and determine my extreme values at this point as well. So using my first derivative test, I know if it goes from up to down, it must be a max. And from down to up, it must be a min. And again, up to down must be a max. So I've got all these. I was a little lazy. I didn't bother figuring out what the y-coordinates were. But remember, your numbers here on the number line, these are your critical numbers. The y-coordinates that match with them are your extreme values. So whatever you get when you plug negative 3 into your function, that would be your minimum. And when you plug 0 in, whatever you get, that's your minimum. And f of 3 is also minimum. Same idea for maxes. That's the first derivative test that I chose to use. So if I continue on, we're supposed to look at concavity and points of inflection. So I'm going to need the second derivative. Well, this was my first derivative. I'm going to have to do quotient rule again. And quite honestly, I just didn't have the patience for that. That just looked not so fun to me. So I started writing it out and I thought, oh, this isn't really going to simplify looking very good at all. So I gave up and I grabbed my calculator. I would expect you to draw the same conclusion. Okay, so if I'm interested in where are the points of inflection, it's when is the second derivative 0. So what I did was I basically said I want the derivative of this equation equal to 0, solve, and I got two values, but 3.325 is outside of my domain, so really I just got one value. So here in my domain for this problem from -3 to 3, there's just the one number, which is 1.563. And if I check on the intervals to the left and right of that, in my second derivative, so I have to actually, when my second derivative comes out positive or negative, it goes plus and then minus. So the plus here in the second derivative number line tells me where I'm concave up. The minus is telling me the section that's concave down. So that's this part over here. These are intervals. Okay, that was it. I hope all that made sense to you. Thanks for listening as always, and I will check in with you guys in class tomorrow. Thanks.